Okay, so we're going to start the recording. I want to make sure I record this so I can post this later. So we're a little bit into it, but you know, hopefully this has all been reviewed so far. So here we're going to go and get back to the PowerPoint. Okay, share that again. Find the page we're on. There we go. Open that up. And okay, we're back to it. Okay, so we've got these solutes that dissociate are ionic compounds and acids, and the ones that don't are going to be covalent compounds. So when you see things that are all non-metals, right, those are covalent compounds. That's one of those reasons why you want to know that covalent compounds are formed from only non-metals, right? If they're only non-metals, then you identify them as covalent compounds. You know they don't dissociate, so they won't conduct electricity. Whereas if you know it's a metal and a non-metal, or if it's an acid, and we'll have more for identifying acids, but what we know about acids right now is that we have a compound that has hydrogen in it, and that hydrogen is going to be attached to a certain other atom that makes the bond actually very similar to an ionic bond. And we'll talk more about that, right, as we start to look at bonding later on as well. But we can identify acids like the halogens, right, so hydrohalogenic acids, and the oxygen-containing acids that we did in the nomenclature section. So that should be how you identify ionic and acidic compounds versus covalent compounds, okay? When we have electrolytes, if you have an electrolyte, it can be subcategorized into strong or weak based on the extent of dissociation. And so if something, if we look at the extent of dissociation and strong and weak electrolytes, if something breaks apart, right, these ions break.
Oh, hello?
What's up?
Sorry, I was touching my mic. I just had a question about printing. So if we don't have access to a printer and turning in labs, like I was printing from the library and whatnot, and everything seems to be closed, do you recommend that we just write the question down, or we actually write on the PDF, download a program to write on a PDF? I'm just thinking about, like, especially labs.
Okay, so let's get through the lecture portion. So can you write that question down, and can we talk about that sort of toward the end of the day? So, and that's a really, I think, a good thing to talk about, because we can troubleshoot that a little bit more also. But if we do some logistics, so we'll stop, you know, maybe 9:15 or something, and we'll take another 10 minutes at the end if any questions come up about sort of logistics. For right now, I'll tell you there are potential ways that we can do that where you don't have to print things in order to do it. So like you could write the answers down on a sheet of paper along with the question number and be able to take a picture of that and upload it. Because since we all should have cell phones where we can do that, PDFs or JPEGs are going to be okay. Right? But let's come back to that, like I said, at the end, in case there are any other questions that are along the same lines. All right. Back to it. Okay, so we're in strong and weak electrolytes. So when they conduct electricity, lost that. When those electrolytes conduct electricity, right, the ions are moving back and forth, depending and facilitating the charge transfer, electrons movement. When you think about strong electrolytes, there we go. So strong electrolytes, we say that they dissociate completely, right? So they all break apart, right? Or 100% of the electrolyte that's in the solution is going to break apart. And so that's an assumption we make. It's not a perfect assumption, and that assumption, we'll see why it's not perfect, assuming we have time to get to chapter 11 and look at solutions and what's called the Van't Hoff factor, whether it's ideal or the actual version. But in general, if you have a strong electrolyte, it's going to break apart. And so we consider it all to break apart. Things like that are going to be things that we consider to be very soluble ionic compounds, like sodium chloride, magnesium chloride, potassium hydroxide, basically things that have alkali metals as the cation, so sodium and potassium, things with lithium, and a number of alkaline earth metals with things like halogens. There's a number of ionic substances. We'll see how to determine whether they're soluble or whether they're strong electrolytes, essentially by looking at solubility rules, which are things we're going to talk about in here in the lecture, but you also have that on your equation sheet for the exams as well. Okay, so that's something you'll see on the equation sheet if you download that. The other type of strong electrolytes, besides really soluble salts, right? Remember, a salt is just another name for an ionic compound, right? The other type of substances are things like strong acids. So the hydrohalogenic acids, other than hydrofluoric acid, so hydrochloric, hydroiodic, hydrobromic acid, sulfuric acid is one of the examples here, but there are other oxygen-containing acids that are also strong acids, one of those being perchloric acid. Those are going to dissociate completely. So if it's a strong acid, it's a strong electrolyte. Weak electrolytes, we're going to find, don't dissociate all the way. So whereas we say a strong electrolyte totally dissociates, a weak electrolyte will still dissociate. But it turns out some compounds that are weak electrolytes just, they only dissociate a little bit. And so some things are soluble because of other rules that we'll look at when we talk about intermolecular forces in the future. And even though they're soluble, they dissolve, but they don't necessarily break apart much. Some examples of those would be weak acids. Weak acids, they dissolve, but only about 5% of those weak acids will dissociate. They're going to stay as intact molecules that dissolve based on polarity of the molecules rather than the dissociation of the ions. Whereas if you have ionic compounds that are weak electrolytes, they're just going to be very, very much insoluble. Something like silver chloride. So we will consider silver chloride to be insoluble. You guys have already had a lab where you've used that. But it turns out that silver chloride is ever so slightly soluble. Now, so what that means is it breaks apart a little bit, or a certain very small percentage will break apart, so it won't be good at conducting electricity, but it'll still potentially conduct a little bit of electricity. So those are your differences between those strong and weak electrolytes. And so we looked at these in class, right? We're still on the in-class stuff here, right? Where we basically, we've used a couple of different PhET simulations, right? Those simulations we talked about. So there's a list of the simulations. There's that are in the general chemistry category. Pointer back. There we go. So the visible pointer here. So if you click on any of these, it should take you to the PhET website. Just directly, right? And so here's the list of those simulations. The ones that we looked at were, if we scroll all the way down to the bottom, the salts and solubility was one of the two. And so you can play around with this. This one requires a JavaScript. And the other one we looked at was, make sure I've got that right. The other one we looked at was the sugar and salt solutions, which is what we use to talk about having electrolytes or non-electrolytes. So I'll let you play with those at your leisure, but those are things we talked about in class the last day we were in class, okay? Then the other thing we did, we talked about composition of solutions. So understanding that when we have a chemical solution, right, this homogeneous mixture, understanding the amount of solute per amount of solvent is really important for understanding how much stuff we can do or make in a chemical reaction. So when it comes to stoichiometry of reactions, understanding the composition of solutions is going to be of utmost importance. And so molarity, right? Molarity is defined as the moles of solute per liter of solution, or the moles divided by the volume. And you get an average number of moles per liter. Just like in density, you get an average number of grams per volume. In that case of density, it's usually grams per milliliter. So the other things we have here, I know we went through these in class as well. Just some definitions. really qualitative definitions so that we know what we're talking about when we talk about a solution as being dilute, right? It has a low concentration, or it's concentrated, it has a high concentration. So if we're comparing two solutions, a solution with a higher molarity will be more concentrated, a solution with a lower molarity will be more dilute. If we consider dilute to be a verb, okay, if we were to dilute a solution, we would make it less concentrated. We would add more solvent to it to do so. The number of moles of solute will stay the same if we dilute something, but the volume would change because we add more solvent to that solution. A solution that's saturated is a solution that's at the upper limit of its concentration. So basically, a saturated solution has the most of that solute that you can possibly dissolve in that solvent. And that's something that is potentially, it's a little bit temperature dependent. It's something that you'll play with a little bit more in a 102 class from a quantitative standpoint than what we will in our class, okay? We also talked about making solutions, right? So one of the important things about making solutions, and so there's a procedure listed here on how to do it, right? If you have a salt or solid, you would take that solid, you'd put a little bit of the solvent in there, you'd pour the solid in, dissolve that solid, right, until it's nice and dissolved, and then you'd fill that, that flask up to the line that's marked on it for the volumetric flask. So you'd also want to generally use volumetric glassware or something that gives you good precision in your measurement. And so you'd put a little bit of water in, you'd put your solute in, you'd mix it up really well, and then you dilute it to the volume that you're looking for. In this example on the screen, a 1 liter or 1,000 milliliter volume, okay? And that the reason you don't fill it up to the line first and then add your solute is because then it would make the solution a larger volume than what you're trying to measure. So if the line was here on this, right, if you were to then put your solute in, right, the level of the liquid would go up past that line and you wouldn't have a solution with the correct volume. And so that order is important for making solutions. Unfortunately, it looks like we won't be doing that in lab anymore, so we won't get that experience. We have a couple of examples in here, and so here's sort of a time for me to test out how well we can do some example stuff. We did a bit of this in class. And so let's see how this cursor works. Hey. And we'll make sure it's all in black. Okay. So the first example, we're going to have a number of pages with example problems. And so the example itself is going to be written at the top, and we'll fill in the blank page as we do our calculation. So this one is one that we did in class, right? How many grams of sodium chloride are there in a 500 milliliter, excuse me, a 0.5 liter solution of 1 molar sodium chloride, okay? And so here, something that we want to keep in mind, and we'll talk a little bit more about this in a minute, is the fact that if you multiply a volume times a concentration, so in this case, right, if we multiply the 0.500 liters, so there's our volume, by the concentration, so 1.00. When I tend to do this, I tend to write in my molarity units as moles of sodium chloride per or over liters of the solution, okay? And so your liters cancel out, right? And that gives you, in this case, right, 0.500 moles of sodium chloride. Again, my writing is going to get better, I hope, in order to make sure we can really follow all this stuff, and I'll try to make it smaller and a little bit better. I'm actually playing with a stylus today to see which side I like to use better, so just bear with, please. And so once you have the moles of solute, of course, you just multiply that by the molar mass. So here, if we multiply that 0.500 moles of sodium chloride by the molar mass. So the molar mass of sodium chloride is 58.45 grams of sodium chloride per mole. You wind up with a value of 29.2 grams of sodium chloride. Okay. And so that should be something that you've done, that you remember from before. Hopefully that's in your notes from before we left 2 weeks ago. Okay. The second part of that, well, what is the ion concentration of a 1 molar sodium chloride solution? And so the important part of this is understanding the chemical equation that governs the dissociation. So with something like sodium chloride, okay, let's try this again. This pen is not working as well as I would hoped. Okay. That's not what I wanted to do. Okay, so sodium chloride, there, okay. We remember sodium chloride dissociates into sodium ions. So sodium plus, there it is again. Right, that are aqueous plus chloride ions are also going to be aqueous. So what we know out of this is that for every 1 mole of sodium chloride, we get 1 mole of cations and 1 mole of anions, or 2 moles of ions. Right? And so what we can do here is now we can say, well, for every 1 mole of, if we look at this, right, 1 mole of sodium chloride per liter of the solution, right? And there's the SOLN is my abbreviation for solution, right? And I know that for every 1 mole of sodium chloride, I get 2 moles of ions. That means that I'll have, if I have a 1 molar sodium chloride solution, it'll be a 2 molar ion concentration. Okay, and that looks terrible. Okay, and so that's a way of doing just the ion concentration for a solution. Now that's going to be important because the ion concentration tells you the concentration of the number of particles dissolved in a solvent in your solution. And that'll come into play more in chapter 11 if we get there, okay? All right, I'm gonna take a pause here for a second. And I wanna check in with you guys, see if are we all on the same page here? Hopefully you're able to write down your notes and better than I can write on the screen at the moment, but hopefully that'll also get better. Okay. So as we continue. Here we go. All right, we're gonna find our way to, let's see, dilution. Okay. So Dilution. So when we were talking about to dilute something, right? Dilute as a verb. To dilute something means we're adding some sort of volume of solvent, okay? And what happens is that creates a decrease in the concentration. So the number of moles of solute stays the same, but the concentration of that solute will be smaller. And so we can use this relationship where if we take concentration times volume, we get the moles of solute. Since that's going to be the same before and after a dilution, you can use that relationship to say, well, if you have a concentration times a volume before the solution is diluted, right, you get the number of moles. And that, because that doesn't change, the number of moles doesn't change, the number or the concentration times the volume after a dilution or after a volume of solvents added is going to equal that, right? And so we say that's M1 V1 equals M2 V2, where M1 is the initial concentration, V1 is the initial volume of that solution. So you multiply those together, you get the moles of solute. M2 is the final concentration after the dilution has occurred, and V2 is the final volume of the solution. So the product of M2 and V2 will be the same as the product of M1 and V1, only here M2 will be a smaller value than M1 is because it's more dilute, the lower concentration. V2 will be larger than V1. And so V2 will be essentially the initial volume plus the added volume, okay? And so we talked about that as being important because there's some language on here, and some of the next example questions that we have are just to sort of get us more familiar with some of the language of this. So we're kind of rehashing a bit of this to make sure we're all on the same page here. So we look at our example question, right? What is the new concentration of a 150 milliliter aqueous solution of 0.250 molar sodium hydroxide in 1 liter? What is the new concentration after it's diluted to 1 liter? So we have 150 milliliters of 0.250 molar sodium hydroxide. We're going to dilute that to 2 liters. Sorry, I've got my little icons here. Maybe we can move them out of the way. Hard to see this sometimes with where these things are lining up. So I apologize if that happens. There we go. Now I can read it. Okay. So for this one, what tends to be very useful as we're doing these types of questions is when you read through a question and you identify how the question or what the question is, oftentimes the most useful thing to do to start to solve it is to say, well, what kind of question is it? What equations are involved in solving this? So in this case, when we're talking about a dilution question, it's often useful to, first thing, come over here and write down the equation that you're going to use for the dilution. There we go. And so here, the equation we're going to use is M1 V1 equals M2 V2. And just writing that down sort of can start to get you organized to solve one of these. And so what I tend to do is then list M1 equals V2, V1, start there, equals M2 equals and V2 equals. And then I go back up to my question and I start to fill this stuff in. Now, so this asks, what is the new concentration if 150 milliliters of aqueous sodium hydroxide? So here we can say that M1 is 0.250 molar. Okay. The initial volume, 150 milliliters, 150.0 ml. M2 is what we're looking for, right? What's the new concentration? So here is what we're looking for. And then V2 is this 1 liter, okay, which is 1,000 milliliters. And I'm going to mark here, and I convert that to milliliters because you'll notice that that's already in milliliters there. And as long as we have those in the same units, the cancellations will work to make the calculation very easily. I underline that 0 here just so I know, right? So that I know basically from this here, right, the initial or the final volume, I've got 2 significant figures in the final volume, right? So I want to underline that just so I remind myself how many sig figs there are in a given calculation, right? And then we just plug these in and solve. And so we take and say M1, 0.250 molar, V1, 150.0 ml is equal to, we don't have M2, so we can just put that in as a variable. And since the 150 milliliters is measured in milliliters, we'll put in 1,000 milliliters as our volume. And again, underline that third 0 so we know where the sig figs are. And then it's a matter of just doing math, right? Dividing by 1,000 milliliters, right? And you wind up with calculating, and you plug this into your calculator at this point, you wind up with a value of 0.0375. Don't forget your units, molar, right? Because the milliliters here cancel out there, milliliters there, cancel out there. And so as long as you're in the same volume units, you're fine, right? And then you've got your calculated answer, okay? So that's one way a dilution can be asked. Another way, what is the new concentration if 425 milliliters of water is added to the 750 mils of an aqueous 12 molar HCl solution? So again, we're saying, okay, we need to identify what type of a question this is. Oh, it's a dilution. Okay, if it's a dilution, we're going to write in M1V1 equals M2V2. And then we say, okay, M1V1, M2V2. Okay. And so our M1, okay, so we're adding 425 milliliters of water to the original volume. So 75 milliliters is our original volume. So we can plug that in here, 75.0 ml. Our original concentration, right, is the aqueous solution that we have. So 12.0 molar HCl. M2, well, we're looking for the new concentration, so we don't know that yet. And V2, so V2 here, this is where it can be tricky. It's not 425, right? It's 425 and the 75, right? It's the V1, so 75.0 milliliters plus 425 milliliters, right? So that's where we have to be careful here, is make sure we remember that V2 is the total final volume, not the added volume. So this is going to be 500 milliliters, okay? And then you just plug them in. M1, so 12.0 molar. V1, 75.0 milliliters. It's a 7, honestly. Is equal to M2 times V2, which is 500 milliliters. And then we just do our math. Right? Divide by our 500 milliliters. Right? And you should come out with a value along the lines of M2 is going to be 1.80 molar HCl. Okay. So that's sort of the second way that these questions can be asked. Another way, it's kind of an easier way, and my opinion, if we actually come back to this page, is if I were just to tell you that this, hold on a second, right? So if I were just to tell you that the solution was diluted to a volume of 500 milliliters, right? Then I wouldn't need to know the added volume plus the initial volume if it was diluted to a certain volume, right? So this solution is diluted to 500 milliliters. And so if I was just given that the solution was diluted to 500 milliliters, I just plug in the 500 milliliters right there, right? Sort of like we did in the previous question. Okay. So going on to our next example, we can use dilution problems to determine, so for example, if we wanted to make a solution to use in a laboratory, maybe you do some research where you need a specific solution of something to mimic something like a biological system. And so you say, okay, well, I want an acid concentration that is a certain, or an acid that's a certain concentration. So the acid that I want is, I want it to be 0.125 molar. Okay, so this question says, what volume of 6 molar sulfuric acid stock solution is necessary to make 2 liters of a 0.125 molar solution? And so the target concentration is 0.125 molar, and the target volume is 2 liters that you're making from a stock solution. The stock solution is just what you'd have handy at any given time. And so in this type of question, you're making a certain volume because maybe you need that much for the process you're doing, and you want that concentration to be the 0.125. But what you start with is what's available to you. And so you're going to do a dilution question to figure out what volume you need of that stock solution. So again, if we notice that this is M1V1, try this here. Equals M2V2, and you list things again. All right, so we know that our initial concentration is this stock solution. So that's 6.00 molar. V1, well, it says what volume of that stock solution, so that's what we're looking for. M2 is 0.125 molar, right? That's this concentration here that we want to target. And V2 is the volume that we have there, so 2.00 liters. And then we again plug these in and solve. So 6 molar times V, try that again, times V1 is equal to 0.125 molar times V2, which is 2 liters. And we just divide by the concentration. So 6.00 molar. And you get V1 is equal to, let's see, 0.0416 liters, or 41.6 milliliters of that stock solution, right? Boom. Okay, so those are a couple of ways that these dilution questions can be asked. Okay. And that sort of brings us to where we stopped before the last exam. So when I last saw you, basically, for a lecture. Okay. So that brings us into section 4.4. All right, so I'm going to pause here for a moment. Okay, so how are we doing? Any questions to be answered now? How are you guys doing? Nothing? You guys remember this stuff, I hope? And so now we're on to new course material. Again, this is, it's a little different way of putting it together. The writing on the screen is hopefully going to get better. I'm not totally sure yet, but we'll see, right? So now we're into some new stuff. Now we're going to talk about, with all of that, all of the background on concentration, we're going to talk about some chemistry of solutions in here, okay? So we'll come back to this. PowerPoint. We got about about 15 minutes worth of stuff to do. So we're going to get a little bit ahead of where we were before, but not super far ahead. So 4.4 is really a short section here. Really, it's just an outline of what we're about to do. So 4.4, types of chemical reactions. And so precipitation reactions is where we're going to start. In a precipitation reaction, right, solid product forms when two aqueous solutions are mixed. So essentially you have, so an example is over here at the right, silver chromate, which is insoluble, and you know it's insoluble because of the S there, right? That gets produced when you mix two solutions. And so the two solutions that you'd mix would be something like silver nitrate and sodium chromate. And so in this solution here, the sodium chromate is going to be this yellow solution, and the silver nitrate is this more clear solution up top. And when you add them together, what happens is the initial solutions, right? This yellow solution, it's clear even though it's colored, right? It's not colorless, but it doesn't have any solid in there, right? You could see through it. It just happens that it would have a yellow tint to it. The silver nitrate, same idea, only that's both clear and colorless. When you mix them together, you form this red precipitate, and that precipitate is the solid product that's formed in that chemical reaction. One of the things we're going to look at is how to describe a reaction that comes from those two aqueous solutions being mixed to form a solid. Then we're going to look at acid-base reactions. And so in an acid-base reaction, an acid reacts with a base, and in the majority of things that we're going to look at in this class, we're going to look at the production of water and a salt. So, or just any ionic compound. And the salt that's produced depends upon the acid and base that are reacting. And so what we won't be doing in lab now is a titration, but hopefully we'll have access to Labster where you'll be able to do a titration in Labster. And basically the idea of a titration, it's a stoichiometric reaction of an acid with a base. Basically you add say a base to a sample of acid that has an indicator in it. The indicator changes color when you have that stoichiometric reaction. So essentially when the moles of acid and moles of base are equal, okay? And so when you do that, when an acid reacts with the base, it forms water and the salt, and we'll look at those chemical reactions in here as well, okay? We'll also look at oxidation reduction reactions, okay? So an oxidation reduction reaction is what happens is there's a change in oxidation state. So you guys did oxidation states in that nomenclature lab. It wouldn't hurt to go back and look at that and see that, or see how to do that again, review a little bit of oxidation states, which we'll do more in the future as well. But for now, it'd be a useful thing to go look at that just before we get to this. So maybe before before Wednesday, for example. But basically what happens is oxidation states change. So something is oxidized, something is reduced. In this example down at the bottom, if you were to put a piece of zinc metal into a copper sulfate solution, so the copper sulfate solution, see, has this nice blue color. If you were to let it sit there, a reaction would occur whereby the zinc solid dissolves and copper gets plated out on that zinc surface. And so when that happens, right, the zinc dissolves, the copper is this reddish, orangish color, right, the copper color, if you will. But you'll notice that the blue color of the solution is a little bit lighter because the copper is plaquing out, right? It's plating out on the zinc surface. Now, this is something we're just going to look at from a really minor standpoint in this class. But in Chem 102, you'll look at this in a much more substantial way, okay? So those are the three types of reactions we're going to explore. So the first type, precipitation reaction. Two aqueous solutions, and the key here, and this is really important for us, is containing soluble salts. So I'm going to highlight that because that's really important. In that initial reaction, those soluble salts, right, they're both aqueous, right? So you have two aqueous reactants and you mix them together and you get a solid product as one of your products. Okay. So if we were to look at a precipitation reaction, these are going to be, and here's another term, precipitation reactions are going to be double replacement reactions. Essentially what we're doing is we're swapping cations and anions. And so the way we do that is if you have a chemical reaction between, say, something like sodium chloride and silver nitrate, and you want to predict the products. Well, you can do this sort of a pseudo Punnett square version of this, but basically what you'd be doing is swapping the anion of one, so this chloride, for the anion of the other. So long and short of it, that's what we're going to do. Now, the way you can do this is you can do it by making this fake Punnett square thing over here. And the way we're going to set this up is you put the cations on one side and the anions on the other, right? So hopefully you guys know what a Punnett square is from back in, I don't know, like elementary school biology when you studied Gregor Mendel and his pea plants. But here what you do is you say, well, let's take the cations, right? So here's sodium, right? Sodium plus and silver plus. And let's take the anions and put those here. And if we combine those two, what's the compound we get? So sodium chloride is one of them, right? That's one of our reactants. But if we were to say the silver and the chloride to react, that would give us a different compound, right? Or if you take sodium and nitrate, that gives us a compound that's not one of our reactants. And then you get silver and nitrate just by playing around with the cation-anion combinations. And so what you'd want to do here is you'd want to say, essentially look for the ones that aren't your reactants, or find your reactants and cross them out, right? So what we do know is that sodium chloride and silver nitrate are reactants, so they're not going to be the products. And so you have two products here that you can list, right? So sodium nitrate and silver chloride. Now what we don't know yet is we don't know solubility, except you guys have done a solubility with, your gravimetric analysis lab, you did stuff with silver chloride. So you know that that's going to be insoluble. But without knowing that it's insoluble, you could at least come up with the two products for this reaction in that way. Now, the next step is predicting what your precipitate will be, predicting what the solid will be, okay? And so in this case, we can use the solubility rules. And these are the solubility rules that you're being given on your exam as well, okay? So we can predict it using these rules, understanding that rules 1 through 6 should be taken in that order. So rule 1 supersedes rule 2, which supersedes rule 3, which supersedes rule 4, etc. So our first rule, most nitrate salts are soluble. Second, most salts containing alkali metals and ammonium ions are soluble. Third, most chloride, bromide, and iodide salts are soluble, with some exceptions. So if they're soluble, that says that they're going to be aqueous, right? So that's a key here, right? Soluble is essentially aqueous, okay, as our as the phase in the chemical reaction, right? If it's insoluble, and so the exceptions, right, would mean that it's insoluble. Okay. The exceptions mean it's insoluble, which it means that it's going to be a solid. Okay. So if you have something like rule 3 that says most chloride, bromide, and iodide salts are insoluble, and you have some exceptions, that means, well, and silver plus is an exception, that means that AgCl, right, is going to be a solid. Okay? And so we continue through the rules. Most sulfate salts are soluble with some exceptions. Most hydroxide salts are soluble with some exceptions. And then most sulfide, right, sulfide being S2 minus, carbonate, chromate, phosphate salts. Those are going to be only slightly soluble. And so for us, generally, we are going to consider the slightly soluble salts to be insoluble. And so this is really just from a qualitative standpoint. These are all qualitative rules for determining the precipitate in a reaction. All of these salts have some measure of solubility. Even if that solubility is very, very, very low, they all have some measure. Now, that's something, again, you'll explore more in a Chem 102 class if you go on to 102. So here, what we can do is we can look at our two products, right? Sodium nitrate and silver chloride. Rule number one, right, says most nitrate salts are soluble, right? So as we look at rule number one, right, that tells us, well, we have a nitrate salt here, right? That's an ionic compound with nitrate. So that's going to be aqueous. So, okay, so sodium nitrate should be aqueous. And so if you go down to, if you rewrite the equation, you're going to want to put in, oh yeah, sodium nitrate, that's aqueous right down here, right? So, yeah, we now have the phase of the sodium nitrate. Now, if you go down to rule 3, right, which we just talked about, right, most chloride, bromide, and iodide salts are soluble. So silver chloride is one of those exceptions. And so we know that silver chloride is going to be insoluble, which means it's going to be a solid, okay? And so that allows you to complete this equation, okay? And that's how you're going to do that for just identifying the products and identifying a precipitate. And so we can do an example here where we can predict the products and the precipitate for a given chemical reaction. In this case, the reaction of lead to nitrate and potassium iodide. So you can see that things like, so lead to nitrate, right? So lead 2, we need to know that it's lead with a +2 charge, and nitrate, we need to know our polyatomic ions, if that wasn't clear before today, right? So make sure you have those. And so you'll get that reacting with potassium iodide. And so what we can do is we can start our chemical equation. We can say, okay, lead nitrate, lead Pb, but it's lead 2+. And so we've got our nitrate, which is NO3 - 1. And so we know that we should have 2 nitrates for every 1 lead, right? We know that this is an initial reactant, and so that's aqueous. Okay, do the same thing with the potassium iodide. So potassium, K, I. Potassium is +1. Iodide is a -1. It's a halogen, right? So we have an alkali metal and a halogen. These are going to be +1, -1, so we're done there. And we'll put in aqueous. Okay. Now this reaction will go to form. So this is where you can, if you are really good with this, you can say, well, I'm going to combine my nitrate and my potassium, right? You don't need to do the Punnett square like we did with the other. And I'm going to combine my lead and my iodide, right? And so if I have the potassium and the nitrate, or the lead and the iodide, we'll take our lead, so Pb. So that's lead 2+ with iodide. Iodide is a 1-, so I need 2 of them. Oh, sorry, I just totally messed that up. I was getting ahead of myself here. There we go. That's what I was trying to do, is just this. Okay. Plus, we've got our potassium nitrate, so K NO3. Okay, and we put our sort of empty parentheses there for the phases. And then we can go back up to our rules for the solubility, right? So we go back up here, solubility rules, right? We know most nitrate salts are soluble. Well, here we have a nitrate salt, right? So we know that that's going to be aqueous. Okay. Then we have a lead iodide. So we have a halogen, right? And we have lead. So if we go back up to these rules and we say, okay, most chloride, well, there's iodide. So those tend to be soluble, except one of our exceptions is lead. So PbI2 is insoluble, therefore it's going to be a solid. Okay. There's one other thing we have to do here, right? Which is just to make sure it's a balanced chemical equation. So if I have one lead there and one lead there, right? One lead on the reactant side, one lead on the product side, okay? That's balanced. I've got two nitrates on the reactant side. I only have one over here, which means I need a 2 on the product side, which means now I have 2 potassiums on the product side. I've only got 1 on the product side here, which means I need a 2 there. And I look at my iodide, I've got 2 iodides, and I've got 2 iodides on the product side as well. And so that leaves me with a balanced chemical reaction, okay? And so now we should be able to predict products and which one is the precipitate. So the precipitate, right, is the lead iodide. Okay, and we abbreviate precipitate often PPT. Okay. All right, and as I told you, we would pause at 9:15 to see if we can answer some other questions. And so we'll pick up there. Now that we know how to predict a product and predict the precipitate in a chemical reaction, now we can, or what we'll do is in the future, our next class, we'll start to do problems where we start to do some stoichiometry, okay? So with that in mind, give me 1 second. Let's see, 29, hey, we got most everybody here. Let's see, good deal. So who is not? Okay. All right, guys, so I will leave this for some open questions here for the rest of the time. If you feel like you don't have any questions on any of the either material or logistics for the rest of the course, like I mentioned, you know, the COVID-19 tentative schedule is posted on the file section. Some of the grades are going up. They'll go. The rest of the lab grades will go up slowly, and I'll try to finish. I still haven't. You're grading your labs is not my key thing right now. It's not my #1 priority. When I have those graded, all of your labs will eventually be up and posted. Your exam is posted. At some point, if I get into campus, I'll get the exam and I'll get those and either scan them or something like that, so it can give you feedback on your first exam, hopefully before the end of the term. But basically, I mean, this is how it's going to go from here to the end. So hopefully this gets a little bit smoother as we proceed. But if there are any questions, I mean, Maya, did I answer your question earlier?
Yeah, you did. Yeah.
Okay, great.
Is the exam with the if we did like an index card, is that within our grade already?
It is.
Okay.
Yeah, it was pretty good. I think as a class, I think you guys averaged like 76%, which is pretty solid for an average on a chemistry exam. So pat yourselves on the back a little bit on that one.
A question for the lab that's due on Thursday. Mm-hmm. If we didn't get anyone else's data for part C.
Don't worry about it. Yeah.
Okay. So just fill in what we have, A and B, and then the questions?
Yeah.
Okay.
We don't have class tomorrow, correct?
That's correct. Yeah, tomorrow is Cesar Chavez Day, so we have a day off. If you have questions or anything, you know, by all means, email me. I'm trying to respond to those much more quickly than I did during the normal term. Since everything's at home, basically, I'm trying to check email more frequently. That being said, having my 18-month-old son around means that I go many hours often without looking at email. So be patient, but I'll try to get back to you as quickly as possible. And I'm still up super early so I can get work done in the mornings and submit stuff before he, wakes up. So I'll try to answer those as quickly as I can generally.
We didn't even know you had a son.
Oh yeah. Trying to get this stuff set up with a toddler around is not the easiest thing. My wife is a 4th and 5th grade teacher, so she's in the same boat.
Question for the lab. You said we have to do questions 4, 5, and 6, and obviously fill in our data. What about the question that says, write a summary of your assessment of the quality of your water sample? That's not one of the laboratory questions. It's kind of like a question before the laboratory question.
Yeah, one sec. Let me go pull that up. I know exactly which part you're referring to.
Because you said not to do D, so we crossed that out. I think that's part of D. I'm not sure.
Let's see. Oh, this is in the answer sheet, right?
Yeah.
Yeah.
That is correct.
Yeah. That one. Oh yeah. Yeah, that's part of D. Yeah. Yeah, so you don't have to do that one.
Okay. Done.
Okay. So the question, where can we find the video recordings? My hope, which by the way, I'm about to stop the recording. I have to get it up onto YouTube. They are not on YouTube yet. As soon as I start to get that up and running, then you'll have those recordings. So for right now, they're not going to be posted until I can get that set up. Again, that's not #1 priority, but it is up there. So I'm going to try that in the next few days. So hopefully those will be posted on YouTube and you'll have a link to all of those in the near future. Okay. All right, I'm going to end the recording right here.